Let's delve into stress at a point here. So what we're gonna, in general, stress. When we talk stress in an engineering context, we're referring to how intense the internal loading of that object is. So the concept of average stress is fairly simple. Load divided by area. Whether or not we're talking, pulling on something, so applying a tensile force, then that's just the load divided by the cross-sectional area of that thing. If we're talking shear, then say if I'm holding this pen here and pushing down on this one side, then I'm applying a shear load, and that's also going to be essentially be shared over that area. Now, unlike the tensile stress, it's not going to be shared as evenly, but even the tensile stress can't really be said to be shared completely evenly because there's going to be some distribution of the some uneven distribution of the load. As you saw from last year with St. Bennett's principle, is that kind of the further you are away from where the load is applied, the less intense those the more evenly distributed it is. Whereas shear kind of varies based upon the position in the object. But anyways, when we're talking stress, we're talking the localized internal loading of the object. So it does vary with position, and we want to be able to represent that somehow. So basically, because when the localized stress is high, then that could be a site where we're going to see failure occur. So these are all caused by external loads being applied to the object, and I mean, external loads could be something as simple as the weight of gravity. So you have a cup sitting here; it's being pulled down by gravity. I guess you could kind of consider that to be a bit of an it's an internally generated external load. Each individual atom of this ceramic cup here is being pulled downwards by Earth, and then all that weight, the fact it's a relatively rigid structure means that the atoms kind of at the top are going to want to fall down, but they're resisted by the rest of the structure. So they push down on the atoms beneath it, which push down on the atoms beneath it, so on and so forth, which means that the internal load is going to be increasing as we get further down. And then when we get to the bottom, then it's supported by a normal force from my hand in this case, or a desk, or what have you. Those internal loads get distributed throughout the body, which allow the transfer of forces. So, whether it be gravity, whether I'm pushing it on here, whether I'm holding it from here, there's a different distribution of the forces that arise based upon kind of where the external loads are applied. So if I'm holding it by the handle, then you're going to see different stress levels kind of in the handles than you would if I was just doing this, because in this case the handle only needs the handle itself only needs to hold the weight of the rest of the handle, whereas here it needs to hold the weight of the entire cup and all the coffee inside. Delicious. So when we're looking at loads, so if we take a body that has some forces applied to it kind of on one end, here and here, and slice it in half, and obviously if for this thing to be in equilibrium, there would need to be, the rest of the body is going to have some sort of reaction forces holding it in place. So some combination of forces and moments that would hold it in place. But if we just slice it in half, then we got this surface here. And in order to stay in equilibrium, we need to have a force and a moment that is applied to that surface, this imaginary surface we just created by slicing this imaginary body in half. And when we do that, essentially, we're not actually getting point loads here. Like, this force here isn't applied right at that point in the center. And this moment here isn't applied right at that point in the center. That force and that moment are actually the net result of the force distribution over the entire face of the object. So if we slice this up, we're going to have this surface here. We can break that up into a bunch of little. We can break that up into a bunch of little imaginary cubes, and then basically on the surface of those cubes, you're going to have a variety of forces. So in this instance, we're defining z as up, y is this way, x is this way, and those forces can, those localized forces can have z or y or x components to them. So you'll note here that the forces in the x direction and the forces in the y direction, they're acting parallel to the cut that was made, whereas the z-axis is pointed straight out. So those are going to be perpendicular to the cut that was made. Or put another way, the z forces are normal to the face, whereas these are parallel to the face. So we would consider the forces in the y and the forces in the x direction to be shear forces, and the forces in the z direction to be axial or normal forces. And then essentially, we've got these tiny little cubes, and basically what happens is that we just kind of need to add up the net sum of the forces on those tiny little cubes, and when we do so, the total result that we're going to get is this moment in this force. So of course we do that by integrating. So essentially what we've done here is we can take these forces and shrink them down to infinitesimally little small cubes. Infinitesimally little small squares. And that'll tell us kind of what's happening on that face. But we don't need to stop there. We don't need to stop with just that top face. We can keep going. So for example, we can take another slice here. So we already took our top slice and figured out kind of what's happening on this top face. And we take another slice here, expose this face, and then we can figure out what's happening on this little face here. So that gives us kind of two sides of our cube. Well, two sides of a body, and we can slice it again this direction. That'll give us this here. Now we got three faces here. We know that if we want to kind of define a tiny little infinitesimal cube here, in order for that to be in equilibrium, we really only need to know what's happening on three faces. Because basically we know that the forces need to balance. So in order for that to occur, this stress, the force that's happening on the y direction on this face of the cube, when shrunk down such that the area approaches zero, we can take that force and call it a stress, a localized stress, by taking that force and dividing it over a tiny little infinitesimal area. So we call that the localized stress. So we do that for all the faces and all the cubes. So instead of talking forces per se, we're now talking stresses. So in order for this thing to be in equilibrium, this stress on the y face here needs to be equal to that stress on the negative y face. This stress on the z face needs to be equal to this stress on the negative z face. This stress in the x needs to be equal to this stress in the x. And kind of continuing on. The opposite sides of the face, the forces that are happening on the opposite face need to be acting in the opposite direction as what's going on here. So this tau yz needs to be equal and opposite to what's going on here, which we would actually call the on the opposite side on the opposite side of that face. We don't actually call that anything. I misspoke there for a second. So that is not what I wanted to click on. So the forces can be defined kind of based upon a combination of these three forces per face. So 3 times 3. That having been said, they're also not completely independent, because essentially, the normal forces are independent. You can increase those, you can decrease those without affecting things. But this tau yz needs to be the same as this tau zy, because otherwise this cube is going to be rotating. And obviously this thing, we're not representing a cube that's spinning inside of an object. We're representing the stress state of a cube that is static, or at least quasi-static, within an object. So if this cube isn't rotating, then the tau zy needs to be equal to the tau yz. The tau yx needs to be equal to the tau xy, and the tau zx needs to be equal to the tau xz. So we can take those and kind of we're still representing them in a 3x3 matrix. This is our stress tensor. This is what we're using to describe the stress state here. But these are independent. These are linked. Those need to be the same magnitude and the same sign. So the format that we do those is the first subscript that we're using gives the direction of the normal plane that the stress is on. So here we've got our setup here, where the y is in this direction, x is in this direction, z is in this direction. So we're following a typical right-hand rule here. So the sigma y is the normal force in the y direction, on the face in the positive y direction. Now sometimes you'll also see this posted as uh, um, sigma YY. That's common enough. So that's just telling us that that is on the positive y face and in the positive y direction. So the second subscript is what gives us the direction of the stress. So for any of the normal stress, the those two match, whereas for the shear stress they don't. Come on, let me select that. Okay. So for our shear stress, for example, we've got here, got the tau xz. So that's the shear stress. We use tau for shear stress. That is acting on the x face. So the x face is here, and it's acting in the z direction. And again, if it's acting in the positive z direction, it is a positive shear stress. If it was acting in the negative z direction, it would be a negative shear stress. So for normal stresses, tensile stress is always positive. So again, that matches with what we talked about, because if we have a force applied to the y face here in the y direction, so both the directionality and the face that it's on is y. So they're both positive. That's going to cause that thing to stretch. So that's going to be a positive tensile stress. If we had that negative, then it's a sigma YY. It's still going to be acting on the y face. It'll just be acting in the negative y direction, so pressing inwards. So tensile stress pulls away from the cube, compressive force acts on the cube. So there's our normal stresses, or axial stresses, that are going to be generated. So for the shear stress, again, if the force is on the positive face and acting in the direction of it's on the positive face of the cube. So again, I'd like to make it clear here, when I say it's on the positive face of the cube, I mean that it is on the face of the cube that is kind of pointed towards the positive axis in question. So if it's on the positive face of the cube and it's acting in the direction of the positive axis, in the positive direction of the other axis it's talking about, then that's a positive shear stress. So again, here, if we're looking just at the xy coordinate system, got the front face here, and we're pushing upwards, then that is going to be a positive tau xy force stress. Or on this face here, we've got the front face for the y, so it's a tau y, and it's acting in the positive x direction, and that's going to be positive. And then, of course, the opposite's here. We've got the tau xy, but it's negative because it's acting in the negative y direction. So just to be clear, here, this stress that we're talking about here, that's corresponding to this one here. It's on the positive x face, and it's acting in the positive y direction. And that needs to be equal to the tau yx. So those two values need to be equal, otherwise you're going to be spinning. So if you do, this is dependent upon your coordinate system. So if you switch up your coordinate system, then your matrix is going to change as well. So if you redefine your axes, you pick different different coordinate system orientation, then your matrix is going to need to change as well. So here's kind of two examples where, here the x is this way, the y is this way, the z is this way, and that would be defined as this. Here instead we've got the x, y, and z this way. They're both right-hand coordinate systems, so that works. They're both consistent, but we just kind of, if we were kind of keeping the same cube, we'd need to redefine our coordinate system. So as well as kind of rotating your coordinate system 90 degrees will change the stress matrix. Obviously, rotating your coordinate system less than 90 degrees will as well. Unfortunately, it's not quite as simple. So if we do something like that, if we kind of decide to, say, tilt our tilt it so we're looking at kind of a different axes, then I'll represent kind of how we would go about that. So if we're starting with a cube, let's say that cube has let's say the cube only has forces in the y direction. So I'm just gonna draw the xy plane. I'm gonna ignore the z plane for simplicity's sake. But we've only got stress in the y direction. Now if we take that cube and cut it in half like this, that thing still needs to be in equilibrium. The stress stays the same. We're just looking at a slightly different configuration of it. So it still needs to be in equilibrium. There's still going to be no zero force on this face, and there's still going to be the same amount of force on this face, the sigma y times the infinitesimal, area. And then we just need to have that in balance. So again, if we have this slanted area here, then essentially we're going to need to have some sort of force generating on that face that's generating the same amount of force as is on the other face. So we can have some sort of normal force, and I'm assuming we're going to be assuming we're going with kind of a rotation like this as outlined here. So we're going from here, I'll just draw this up here. We're starting with this coordinate system, x and y, and we're moving to a new coordinate system. This new coordinate system has x prime and y prime. So we'll have some sort of normal force here. We'll call that sigma x prime, because again, this positive face here, this face here would be in the positive x prime direction. And then we're also going to have some amount of shear stress that develops. Because we've got this normal stress here that we're generating. It's generating a force that is it's both up, but it's also over to the side of it. It on its own would be generating a certain amount of horizontal force. So we need to counteract that, and the only way to counteract that is to be representing that with a shear force. So we'll call that tau it's on the positive x prime face. So tau x prime, and it's pointed in the positive y prime direction. So tau x prime y prime. So what we know is the forces generated by that need to be need to add, these two forces need to add up to this force in order to be in equilibrium. So one thing that we're going to need to do is kind of take into account the fact that these two scenarios have slightly different areas because, again, we kind of cut it across. So the area that the sigma x prime and the tau x prime y prime is acting upon is actually going to be equal to the square root of 2 times as large as the stress in the sigma y. But we can add those two up, so it's going to be essentially, and the other thing that we know is, so if we got this one downward force, and we got this force acting at 45 degrees, and this other force acting, that's also acting at 45 degrees, these two forces, these two forces, those need to be the same in magnitude. Because they're both kind of acting at the same angle. Like, I mean, it's 45 degrees from a different axis, but they're acting, they need to have the same magnitude because their horizontal components need to cancel out. So the absolute value of the sigma x prime needs to be equal to the absolute value of the x prime, the tau x prime y prime. And then just for our force balance, then basically, so basically the y component, if we kind of look at it in the original coordinate system, the y component of the force on this face from either of those, because they're both the same, needs to be equal to half of the y component of the original force. So basically, so our sigma y times the delta A divided by 2 needs to be equal to the sigma x prime times the its area, which again is square root of 2 times dA. It's slightly bigger because it's angled, but we're looking at just the y component of that. So again, this is at 45 degrees, and this is the this is that term there. So we just, in order to get the y component of that, we multiply by the cosine of 45. So if we want to solve for our sigma x prime in terms of the sigma y, and we just need to, it's relatively simple. So we'll cancel out our dA's here. So that gives us sigma x prime is going to be equal to sigma y divided by 2 times the square root of 2 times cos 45. So just divide out these terms, cancel out the dA's. So let's see, 1 divided by 2 times square root of 2. So that gives us half sigma y. So that's kind of the variation we get when we rotate our frame of reference. So that would be for kind of like a, that'd be what we need to have for that triangle. Now, if we took that triangle, so we know what we need for this triangle. Well, guess what? We can add another triangle to it down here. And we would find, so we found out our sigma x prime, and we found out our actually here, let's not do that triangle there. And we found out our tau x prime y prime. If we do that, we add another triangle here. Same process. Same process would be used, which would find us sigma y prime, and it would find us a tau y prime x prime. And similarly, we could use that to extend that. So essentially, we could use the same process to kind of transform from this to our new rotated shape in terms of the stress levels. So we rotated, this shows us how we're looking at the stress determines how we calculate it. So the angle of orientation of our coordinate system very much so matters when we're calculating that. And we'll touch upon this quite a bit later on in the course when we get to the stress transformations, because what we can do is we can actually take, if we calculate a stress state that has shear stresses all over the place, it turns out that we can actually take that and we can figure out a combination of rotations about the x-axis, about the y-axis, about the z-axis that can be done that will transform any stress state that has shear in it to a stress state, a single stress state that has only normal forces applied to it. So only compression and only tension on that cube based upon what orientation we give it. So we call that the transformation to the principal stress, and those are used extensively when we are trying to figure out, is this component going to fail? Because all of our failure criteria that have been developed are developed in order to allow us to plug in kind of that principal stress, the principal stresses that we calculate into those failure criteria to figure out, hey, is this thing going to fail on us based upon these three numbers instead of necessarily, having to use the 6 independent numbers that we would have in a stress tensor otherwise. So again, we'll be using those later on, but for now, just keep in mind that it's the selection of your coordinate system does matter quite a bit for how you're going to end up calculating your stress state. That's it for now.